So we're going to be covering 7.5 today, independence and the multiplication rule. And we just watched um, the banana video, right? Um, so with that, it says the video mentions the idea of two events being independent, but what does that mean? Chances are that you've encountered this idea of independence in previous courses, right? And so what was the idea of independence? If one event is independent from the next event. What does that mean? It's kind of a challenge, right? It doesn't have to be perfect, right? Yeah. That each result of the probability is its own independent chance, right? And let's just change it to the idea of dependence, right? So if it's dependent, it means that something happens, and then the next thing that happened is dependent on what occurred the first time, right? Or independence, what happens the first time, right, doesn't affect what happens the second time. So I think that's actually a really good way to define it. So two events are independent. So we've got this great definition right here. Um, Two events are independent when knowing whether one event has occurred does not change the likelihood that the second event will occur. The dice rolls in the last banana were independent events because the results of one die didn't affect the result of the other, and therefore should not affect our prediction for the other. If we don't, if we don't believe that one event affects the other, we say that we believe that the events are independent, right? So that would be a good way to put it. However, if we believe that one event affects the other, we say that they are dependent. Okay, so exploration one, right? Um, Independent or not. So several questions are posed below. Each question is about a possible connection between two events. For each question, identify the two events and indicate whether or not you think that there would be a connection. If you believe that one event affects the other, state that they are dependent. If you believe that one effect does not affect the other, state that they are independent, and then explain your reasoning. Okay, so let's just take a look here at A. We want to figure out what are the two events, and then do we think that they are dependent or independent? So it's this first one is, are high school students whose parents or guardians set a midnight curfew less likely to have a traffic violation than students whose parents or guardians have not set such a curfew? So what are the two events? What's event one? Okay. Students with a midnight curfew? What's event two then? Um, it was said students without a curfew. That's actually taken care of in event one, right? Either you have a curfew or you don't have a curfew. That's event one, right? We're just saying it in the positive that the event is that they have a curfew, then implied that there will be students that don't have a curfew. So what's the other event? Ah, there you go. Traffic violation. I'll say have traffic violation. So are these dependent or independent? Okay. You say that they are dependent? Okay, so how would you argue that they are dependent? Okay. So it was basically you can't get a midnight traffic violation if you aren't up to midnight. Is the traffic violation based on time? I would argue that it's not based on time, that it could be any time of the day based on the wording of the problem. So would that change your answer? Okay. So you would then say that it was independent. And why would you say that it's independent then? Okay. The statement was made that it didn't know how to argue it. Does someone have a thought? Like, would you argue dependent or independent? Let me do this. I'll give you the parent logic. How's that? It is dependent, right? Okay, you can hear your parents. I've got my best parent voice here. It's dependent. I mean, come on, it's obvious. The later you go to bed means the less sleep that you're going to get. The less sleep that you're going to have means the poorer judgment that you're going to have. Poorer judgment while driving means the more likelihood that you're going to be in a traffic accident. Boom. Did I do a good job? Right? Is it fair logic? Yes. Is it necessarily true logic, or is it necessarily a true statement? Could it be argued that they're actually independent events? I think you could, right? And so it would actually be kind of cool to then look at, well, what does the data say, right? You know what my parent says. I know that I don't think that it's necessarily. I think as a student, like I could just hear, one of my kids saying, you know what, Dad, it doesn't matter. Like, yeah, I'm tired, but I still have good logic skills, right? And I won't get in an accident, right? hmm So get the idea. So, and on these ones, we're not saying that there is a right answer. I think we have to like investigate it. So, but it's to get us to think, right? What do we think? And then with statistics, it's about, okay, then how do you then investigate to see if it's true or not? So, I'm going to go ahead, I'll put here, right, whether you agree with me or not. And if you don't agree with me, then you can write independent and write why you don't agree with me. But I'll just say, okay, later to bed means less sleep and therefore poor judgment. How about the next one? Are students who regularly listen to classical music more likely to be interested in mathematics than students who do not regularly listen to classical music? So what's event one in this one? Okay, listening to classical music, right? And what's the other event then? Good job. I'll just write math instead of mathematics, but yes. Okay, great. So then would you say that's independent or dependent? What do you think? Again, on this one, I can argue both ways. Okay, I'm gonna argue independent. If I can spell independent. There we go. Mr. Labus. Oh my gosh. Um, right? and people appreciate music whether they're interested in math or not, right? Appreciate music whether they are interested in math. Some of you might say, well, no, Mr. Labus, surprised you don't know this. Music is actually quite mathematical. And I think that people that are interested in classical music actually appreciate that very mathematical side of it. And so therefore it's going to be a dependent situation. Does that make sense? It actually is, by the way. So event C, that doesn't mean that it's dependent though, right? We need to look at the data. C, are people who play video games more than 10 hours per week more likely to select football as their favorite sport than people who do not play video games more than 10 hours per week? So what's event 1? What was that? Playing video games for 10 hours a week? Greater than 10 hours per week? What's event 2? Okay, I'm going to write like football also because I think that's a nice abbreviation. It's their favorite sport technically, right? I'll write favorite because I have a little bit of room here. Okay, so what do you think? Is that independent or dependent? You what? Okay, I like that. Independent, no correlation. No correlation, I like that word, between playing video games and liking football. Might need to be a little more specific, but why don't we keep moving? How about this next question where it says, give an example of uh, two events as described in the categories below. Okay, so right, give me 2 independent events and 2 not independent, right? So they'd be dependent events. Okay, so for the sake of time, I'm going to say this, right? Independent events. 1, right? Having a lot of goldfish. Okay, and 2, favorite color is green. Any correlation there? Okay, I would say no. How about for the second one, pair of events that are not independent? So they're dependent. I would say, how about study hours for an exam and achieve higher grades? Get the idea? Notice I didn't say achieve an A, I just said just higher, right? Higher than you normally would. Okay, even though we often have feelings as to whether events should be independent, it is important that we use the data when available to evaluate whether they are. And we're going to be doing that in future lessons. So we have the multiplication rule on the next page. The multiplication rule says if we know that two events are independent, then we can apply the multiplication rule to find the probability that the events occur. And this is the probability rule right here, right? The probability of A and B is equal to the probability of A times the probability of B. Okay, now that is, right, if they are independent. So we have to know that they're independent before we can apply the rule. Since two die rolls are generally independent, the multiplication rule was used in the last banana experiment to calculate probabilities. This rule can easily help us calculate most of the theoretical probabilities from this experiment. So 3, verify probabilities from the last banana experiment. A, what is the probability that the first die gives a value of 1 through 4 and the second die gives a value of 1 through 4? Okay, so here. So probability, right, that I'll say die 1 is a 1, 2, 4. Okay, and die 2 is a 1 through 4. Are they independent events? Yeah, they told us that they are, right? Die rolls are independent of the others. So then what we could do is we could write this as the probability, right? The die is a 1 through 4, and we can multiply that by the probability that the die 2, right, is a 1 through 4. Okay, well, how many favorable outcomes are there for on a die to get a 1 through a 4? Right? Out of 6, right? And then it's 4 out of 6 on this one. When you multiply those, you get 1636, right? So, and I could divide both of those by 4, which gives me 4/9, which on the calculator is 0.444. Which player would win in this situation? Right, this situation, right? They're referring back, aren't they, to this part A? So what is it? If it's a 1 through a 4, player 2. It's not player 2. Player 1, right? Player 2 wins if one of the die or both of the die is a 5 or a 6, right? So this is player 1. Okay, so let's take a look is what's the probability that the first die gives a value of 5 or a 6 and the second die gives a value of a 5 or a 6? So notice here, right? So the probability that die 1 is a 5, 6, and die 2 is a 5 or a 6. Well, we know, right? Probability of die, that they're independent events, so we can multiply them together. Die just means a singular, right? Dice. So how many favorable outcomes are there on the first die? Well, isn't there only 2, a 5 and a 6, out of a total of 6? Same thing with this one, right? 5 and a 6 out of a total of 6. That's 4/36. Again, we can divide top and bottom by 4, which gives me 1/9. And I'll just tell you that's 0.111 approximately. So who wins in this one? Yeah, that one's player 2. How about the next one? The only other possibility is that one die has a value of 1 to 4 and the other has a value of 5 or 6. So what's the probability of that event occurring? Well, in part A, we found that both die were a 1 to 4, right? In part C, we found both die were a 5 or a 6. So aren't all the other combinations going to be one die is 1 to 4 and the other is a 5 to 6? Does that make sense? So what I'm going to do here is instead of like trying to figure out, well, what is that exact? I'm going to take the 100%, right, written as a decimal, that's 1, right, and subtract the probability that both die is a 1 to 4. And then subtract the probability that both die is a 5 or a 6. Okay, so this is going to be 1 minus. Now, we did this up above, right? I should pick colors that I haven't used. So this here, right? Both 1 to 4, was this up here, right? So I'm going to take the 4/9 that we got for that one and write it here. Okay, and then both a 5 or a 6. So here, maybe I'll both a 5 or a 6. Well, okay, so let's do that one in this color. So I'll do here, right? That's 1/9. Okay, what's 1 minus 4/9 going to give you? 5/9, right? And then what's 5/9 minus 1/9? So this is equal to 4/9. Do you guys all agree? That looks like here. I'm gonna bump this over just a little bit here. Okay, so it is 4/9, and then as a decimal, I know that's 0.444. So who's gonna win in this case? If they're if one of the die is a 5 or a 6, basically, isn't that player 2? Because the only instance that player 1 wins is if both die are between a 1 and a 4, right? The other person, player 2, wins when both are a 5 or a 6, or one of the die is a 5 or a 6. Is that clear? Is that kind of cool? Okay. Based on these calculations, what's the probability of player 1 winning? Okay. Isn't this just going to be the 4/9 from part A? It's the only way they can win. Which is approximately 0.444. Based on the calculations, what's the probability of player 2 winning? Wouldn't it be, right, from part C, the 1/9, right, plus, and part E, the 4/9. This is part C. And this is part E. Which that's going to give me then 5/9, which is approximately 0.556, right? Because I have to round at that point. The book actually says 555, by the way. Okay, since the two events are independent, the probabilities we just calculated with the ones we found agree with the ones we found, right, by making the table in lesson 1. Can we go to the next one? Exploration, the complement rule. So I used the complement rule already, so they're going to formalize it here. We've been doing it. Even though they did not use the term, the video used the idea of complements, okay, to find the probability of player 2 winning. The narrator noted that since player 1 had a 16 in 36 chance of winning, and the only other option was for player 2, we could subtract 1 minus the 1636, or 3636 minus 1636, to find player 2's probability of winning. That answer agrees with our previous calculation. To find the probability, here we go, right? To find the probability that an event does not happen, you can subtract the probability of the event from 1. If the event is denoted by A, then this can be written as the probability of not A is equal to 1 minus the probability of A. So the probability of player 1 not winning is 1 minus the probability of player 1 winning. Okay. So let's go through this. So the probability of player 1 not winning is 1 minus the probability of player 1 winning, right? Not winning equals 1 minus player 1 winning. For example, suppose that the probability that a particular flight is on time is 7.78. What's the probability that it's not on time? Well, for that to occur, right, we would take the probability, right, not on time, and write that as 1 minus the probability of it being on time. Well, we know in the problem, right, so this is going to be equal to 1 minus, so in the problem, they tell us the probability that a particular flight is on time is 0.78. So we would take that 0.78, right, and we could write it then in this location, 0.78. And we would get that it is equal to 0.22, right? Okay, or, right, 22% of the time. So there's a 22% chance the flight not on time. Okay, so exploration 3, using using the multiplication rule for independent events. Number 5, a number cube has faces numbered 1 through 6. So a number cube, that's a die, right? And a coin has 2 sides, either heads or tails. The number cube will be rolled and the coin will be flipped. Find the probability that the cube shows a 4 and the coin lands on heads. Okay. Now, something that we need to just make note of here. Okay. Notice this. Are these dependent events or independent events? Does the coin flip have any like dependence on the die roll? Not at all, right? So these are independent events. Okay, great. So it says find the probability that the cube shows a 4 and the coin lands on heads. So I'm going to write it this way, right? What's the probability of a 4 and heads? If they're independent, which we said they were, then we're looking for the probability of 4, and we're going to multiply that by the probability of heads. Okay, well, fine. On the die cube, how many 4s are there? Only one. How many total faces are there? Or how many numbers are there? There's 6, right? And then we're going to multiply that by, on a coin, right? How many heads are there? Over how many sides? 2. So notice, isn't this just 1 in 12? Which is approximately 0.083. Okay, or we could write that as 8.3%. Okay, how about the next one? If you toss the coin 5 times, what is the probability you will see heads on all 5 tosses? Okay, so if you toss the coin 5 times, isn't this also going to be independent? And yeah, every time you flip the coin, it's not going to be dependent on the one that we just flipped. Now you might make a guess based off probabilities, right? But it is independent of the previous one. So the probability, right? We're looking for probability of heads, right? And another heads, right? The second one, and a third one, and a fourth one, and a fifth one, right? All 5 of them are heads. If they're independent events, isn't this going to be the probability of heads times the probability of heads times the probability of heads times the probability of heads, and we're going to do this 5 times. Okay, so when we flip a coin, how many heads are on the coin? 1, right, in 2 choices. So is on each one of these going to be a half? That's 1 over, and then 2 times 2 times 2 times 2 times 2 is 32. So if we put that on our calculator, 1 divided by 32, you get 0.031. Right, or a 3.1% chance that when you flip a coin 5 times in a row, that you'll get 5 heads. C. If you roll the cube 3 times, are those going to be independent events? Right, also independent. What is the probability that it will show 4 on all 3 throws? So we're looking for the probability of a 4 and a 4 and a 4. So probability of a 4, right, they're independent, so I can multiply those. Probability of a 4 times the probability of a 4. How many 4s are on a cube? 1. How many faces are there? 6. So it's 1 in 6 times 1 in 6 times 1 in 6. So isn't that 1 in 216? Which if you divide that, it's 0.005. Percent-wise, look at that, right? That's 0.5%. It's only 0.5% chance that you can roll a 4 3 times in a row. Are we okay with that? Okay. Last example. Suppose that a credit card company states that when a customer is selected at random, the probability that the customer pays his bill in full each month is 0.35. The probability that the customer makes regular online purchases is 0.83. And these two events are independent. What is the probability that a randomly selected customer pays his bill in full each month and makes regular purchases? Oh, well, that's going to be interesting. Notice here we have that the probability that a customer pays his bill in full is the 0.35. Okay, and then we also have the probability that a customer makes regular purchases is 0.83. And then we had one more piece of information, that these two events are independent. Do you see that? So if we're looking for the probability that they pay bill in full, and they make regular purchases online, if they're independent, don't I get to rewrite this as pay bill in full times the probability of regular purchases online? Okay, and we actually have pay bill in full. Isn't that what I highlighted up above in orange? And that's 0.35. And this one here, right? Regular online purchases, isn't that 0.83? And if we multiply those together on our calculator, we're going to get 0.291, which is going to be our answer, right? Right, or that's 29.1%, right? Okay, are we good with that? Okay, that will wrap up the lesson.